clickers. Thanks very much. Before I start, I should thank Bob and Prakash for organizing this and inviting me. But of course, we both know that Bob can't organize anything. Prakash travels around the world like a rock star, so whoever did organize this, thank you for doing so. And getting me here. So yeah, I came up with this title while I was in the middle of Central Africa on the dial-up modem, so I'm not quite sure why it was so wrong. And obviously, I was drunk at the time I wrote it. And the work is very much work in progress, so you're going to see some things that are kind of well-formed ideas and some that are very partial ideas. But so, I'm going to start off with just talking about quantum computing in general. I'm not going to give you a real outline for this talk because the talk is, as I said, about work in progress, and it's almost something that I'd like to run from backwards through the talk somehow, sort of start at the end, but I can't quite do that. So you're getting kind of a talk which is everything I can think about, or I am thinking about at the moment, that's sort of somehow related to what's going on in this workshop. So let's start with quantum computing. If you're an old person in quantum information theory, this is how you imagine a quantum computer looks like. Okay, this is the circuit model. This I just ripped out of the Nielsen and Schwan book. These days, if you're a cool, young, hip quantum computing person, you work on this model of quantum computing. Okay? So this here is the measurement-based model due to Rausendorf and Riedel. The difference here is that here we have qubits undergoing unitary evolution in time. As time flows along, these are the same physical systems undergoing some kind of interactions with each other. This here, the physical systems, this is all space. So the physical systems are all these little dots over here and these spins. And what happens is that you push information through an entangled initial state of this system by doing measurements on it. So there's no unitary evolution anymore in this model. The dynamics is all done by collapse of the wave function. That's a really interesting foundational topic, and in fact, there are many people, I think, who think of unitary evolution as really the fundamental thing. If you're a many worlds person, you think of unitary evolution as really the fundamental aspect of quantum mechanics, and measurement is this nasty thing. And you can turn this around and come up with models of quantum mechanics, which unitary evolution is just a coarse-grained, emergent kind of thing, and the fundamental thing that's going on is measurement. So I think that there's interesting foundational lessons to learn from these two different models of quantum computing. So these are the most studied sort of ways of, say, building a quantum computer, trying to understand what we can do with a quantum computer, and so on. Now, if you're mad, you might think that this has something to do with quantum computing. This is a whole bunch of diagrams, and I pulled them out of Bob's kindergarten quantum mechanics paper. I don't really understand what's going on here. I just know that Bob will draw up some kind of diagrams, and he'll talk about letting information flow through this and that. And somehow he doesn't have Hilbert space, but at the end of the day, he wants to tell me that this has something to do with quantum mechanics and quantum computing. So, I'm not as smart as Bob, but there are other smart people out there. If you're a Fields medalist, Mike Friedman thinks that this is quantum computing. Okay? And this is actually a really fascinating diagram, so let me just spend a minute explaining to you what's going on. So Mike is also drawing graphs, or in this case braids, and relating them to quantum computing. And this is a model which is motivated by an implementation. The implementation is we have a 2D electron gas in a particular state, we create excitations, and we thread them around each other, and it turns out we can do quantum computing. But if you're just a mathematician and you don't want to know anything about 2D electron gases and all that kind of stuff, there's just a mathematical game that we can play here. This is a braid, okay? A braid is these strands that run down here, and the strands cross each other with links that go either over or under the adjacent link. Okay? In this case, the way the quantum computing is done, it turns out that they actually put a braid and then the inverse of the braid, one after the other. So it's kind of symmetric when you go this way. And then they close the braid by just connecting adjacent strands. And what they show is that if you have a quantum computation on a certain number of qubits, then you can look at the sort of the circuit for that quantum computation, turn that circuit into, or use a classical computer to draw a braid like this, and then the probability of that quantum computation giving, say, the zero outcome on a final qubit is a function like this of the Jones polynomial of this braid. Okay. Now the Jones polynomial of a braid, or it's just sort of something from knot theory. It's something which really a priori has nothing to do necessarily with quantum computing. Knot theory was studied long before people even knew what quantum mechanics was. Okay. It's interesting that the Jones polynomial itself did come from Jones studying von Neumann algebras, but at some point that's almost a historical accident. It could certainly have been discovered without that fact. But what we have is like a mathematical combinatorial type problem. We've got a braid, we draw it down, we say doing a quantum computation is exactly the same as having this braid and being able to evaluate the Jones polynomial. And it turns out that evaluating the Jones polynomial is an exponentially hard thing. If you try and do it for a knot or a braid, basically every crossing causes the polynomial to kind of double in size. And so in practice, we can't evaluate the Jones polynomial for very large braids. But what Mike Friedman and Kitaev and a whole bunch of people showed was that you can have the output of a quantum computation proportional to the Jones polynomial. These are just kind of factors and sort of slightly irrelevant things here. But proportional to the Jones polynomial evaluated at the fifth root of unity. So your quantum computation can't evaluate the Jones polynomial, or let's say sample the Jones polynomial at arbitrary values, but at certain values, certain roots of unity it can. Okay. This is a fascinating result because it was the first mathematical problem proven to be what we call BQP complete. Okay? That really quantum computation is the same as this and vice versa. And so there's now a few more problems which are known to be BQP complete, but I really like this one. Okay, so this here is yet another diagrammatic way. We've seen what Bob does, we've seen what these guys do. I'm kind of interested in trying to find kind of diagrammatic, combinatorial, whatever, graph theory, let's say, ways of doing quantum computing which don't have a preferred temporal structure. So that measurement-based quantum computing, the temporal structure was put in by the ordering that you're forced into doing these measurements. Obviously, in unitary evolution, there's a really implicit temporal structure. Even in these things, the way they're sort of constructed, the information has to flow in this sort of the same temporal structure in which you're threading these anyons around each other in this whole liquid. So, and in Bob's stuff, from what I understand, you also have a notion of information flow through the structure. So my sort of ultimate goal, and which I haven't, I think, completely attained yet, but is to see if I can almost come up with just a graph theory type problem which doesn't have any kind of temporal structure necessarily associated with it. So the sort of thing that what I'm going to do in this talk is I'm going to show you how to do something like this. You take a quantum circuit. So this is a standard quantum circuit. These are controlled NOT gates. These are some kind of single qubit gates. I input some set of states. This here just means that I'm measuring in the all, I want to know what's the probability of getting all zeros on the output. I'm going to show you how you can sort of draw a graph over the top of this circuit. Okay. So from that circuit you can kind of construct a graph. This at the moment is a little bit figurative. This isn't exactly the type of graph that I will construct. But the idea is basically that in this graph you have loops, and the various loops you can sort of associate with qubits. And then in this graph there are vertices which, there are subgraphs of the vertices which kind of act like quantum gates. Okay? So these things are kind of acting like the single qubit gates. You might have one subgraph. When you have a controlled NOT gate, you might have a different subgraph, and so on. Okay? But at the end of the day, all I have is just a graph. I just draw it on a piece of paper. These sort of boundary conditions here set what the input states were and what the things I wanted to measure in the original circuit were. But what I'm going to show you is that, okay, you can construct a graph like this, and then if you're just given this graph, you can ask, what is the sum of the weighted cycle covers of this graph? Okay, so that's just a standard kind of thing that graph theorists are interested in about a graph. But that the mod squared of the sum of the weighted cycle covers is the same thing as the quantum probability of the circuit. So that if you can sample the cycle covers of this graph, you kind of do the same thing that a quantum computation does. You have an output with whatever that probability is. Okay. So that's the sort of overview of the story that I'm going to tell you. If you want to stop me and interrupt me, please.
What's the weighted cycle cover?
Oh, sorry. Okay, I'll explain a little bit more in a second. It's a few tracking, of course, because I haven't actually been through the talk since I prepared. I couldn't remember what the next slide was. I thought I explained on the next one. It's in a couple of slides' time. So the cycle covers of a graph are just basically loops on the graph which visit such that every vertex gets visited by a loop and the loops don't intersect with each other. So one cycle cover on this graph is like all of these loops, and then in fact this guy would have to have a little self loop and so on. But then there are other cycle covers maybe that go through all the vertices and come back in one loop. So you get some things which are big loops, some things which are little loops. And then each cycle cover has a weight which is just the product of the weights on all the edges. And then the sum over all of those gives you the quantum probability. Anyway, I'm going to go through it in probably excruciating detail in a little bit. But the way we're going to get to constructing this graph is not from the sort of circuit I showed you. We're going to start with a circuit which is built out of only Hadamard and Toffoli gates. Okay, so there's this result of Xi and simplified by people like Dorit that say that every quantum computation can be done by just using the Toffoli gate and Hadamard gates. Okay, the Toffoli gate is the control not gate. You flip this guy if both of these guys are a 1. The Hadamard gate is just the most trivial Fourier transform gate in quantum computing. It takes 0 to 0 plus 1 and 1 to 0 minus 1. Okay, so we're going to imagine that we don't start with sort of the normal quantum circuit. We actually start with a quantum circuit that's like this. And now we're going to use a result that I think should be better known, let's say. But then, given a circuit like this, you can compute the probability of this output by doing what I'm going to call the Boolean path integral. So it's this result from Chris Dawson and collaborators in QuantPH in 2004. And so it's the only sort of place that I know people have really used sort of basically path integrals to sort of analyze quantum circuits. But the way we're going to do this path integral, I'm just going to show you by kind of explicit construction how it works. What you do is you have a path integral over Boolean variables. So you input variables x1, x2, x3, and x4. Okay, and these things are all just zeros, or can all be only 0 or 1, they're Boolean. And then you kind of run through the circuit, and you just follow a simple rule which says that every time you go through a Hadamard gate, make up a new Boolean variable. Okay, so x5 and x6. Okay, and every time you go through a Toffoli gate, the variable that comes on the qubit which gets acted on by the Toffoli gate, what you do is you take that variable, in this case x3, and sum the product of the two guys up here. Okay, so x2 and x5. So you write on the line x3 plus x2, x5, where the addition is done modulo 2. Okay? And now you run through a Hadamard gate again. Okay, so you change, you've got to make up two new variables, x7, x8. You've got to run through the last Hadamard gate. And what you've done now is you've just kind of drawn a whole bunch of Boolean variables all over your graph. And now you follow a rule which says find the Boolean function that I'll call phi of x, which is a sum over every Hadamard gate in the graph, the product of the variable that goes into the Hadamard gate with the variable that comes out of the Hadamard gate. Okay? So I've got x1 times x5, x5 times x8, and so on. So here's this formula, x1 times x5. I go to this one, running along here I've got x5 times x8. Here I've got x2 times x7, x4 times x6. And then this one is where something slightly more interesting happens. Now I get x3 times x9 plus x2 times x5 times x9. Okay? So I get a cubic term here. Everything else is a quadratic term. Okay. So you make up this formula, and then what you would do is, if you're interested in particular values of the inputs and particular values of the output, you would substitute those values into the formula. Unfortunately, I went to all the trouble of drawing this thing and then realized I'd come up with a completely trivial formula. The probability is 0. But you would do this to any arbitrary circuit. Okay, you would go through, sum in these values. And now what you do is that you take this Boolean formula, which is a kind of a Zoran formula. It's basically a cubic polynomial over GF2. It's monotone. There's no negated variables in this formula. And the quantum probability, the sort of output probability to your quantum computation, this thing, okay, so this U means the unitary of the quantum circuit. This is given by the mod squared of what I'm going to call number 0 minus number 1. Okay? And number 0 and number 1 are just the number of solutions to this formula being phi of x equals 0 or phi of x equals 1. So you take that formula and you say how many solutions give the output value 0, how many give the output value 1. Okay? And then your quantum probability is the mod squared of this. And you've got a normalization factor here, which is 2 to the number of the Hadamard gates in the circuit. Okay, so as I said, you can read about that construction. I'm going to sort of take that construction as given. You can read about it in that paper. It's quite simple, actually, once you start sitting there and working through it to see why it works. Okay. So now, if you're a computer scientist, which I'm sorry for you if you are, you might look at it and say, yeah, this kind of looks vaguely familiar. These kind of things sit in the complexity class that Lance Fortner calls GAP-P. Counting solutions to things sit in the complexity class, sharp-P. But thank God I'm not a computer scientist, so I'm going to ignore that for the moment. Okay, so a question I have, and I haven't gotten a particularly good answer to it, is what features of this formula are special due to the quantum circuit thing? Because it is a sharp-P complete problem if you take arbitrary, what we would call Zoran formulas. Okay, there's and, this here is an and, this here is an exclusive or. So it's still unclear to me what's special about the quantum formula. I have a bunch of ideas. I'm not sure they're really important to what I'm going to talk about in this talk. But I'd kind of like to know what feature of doing the quantum calculation or the quantum sampling means that we're not solving arbitrary sharp-P complete problems by being able to approximate this thing. So if there's anyone who's an expert on that kind of stuff, I'd really like to talk to you. But that's somewhat of an aside question. So let me go to now, so now I'm going to jump again, and then I'm going to bring these things together. So what I'm going to jump to now is cycle covers of graphs. Okay, I'm going to explain how cycle covers work. So here's a very simple example of a graph, and the weights on the graph are 1 unless there's another number written there. So the weight here is 1, the weight here is 1, and so on. So I've got a directed graph. I have no parallel edges in this graph, but I have, but it is directed, and I can have self-loops in the graph. Okay. Now the cycle covers of this graph, there's basically 3 different cycle covers. Okay, so the rule for the cycle cover is you've got to visit every vertex, okay, but every vertex once, and you've got to make loops. Okay, the things have to close. So one cycle cover is to go around this triangle with these 3 vertices and let this guy self-intersect. A different cycle cover is to go just around all 4 vertices in the square, and a different cycle cover is to let all 4 of them just self-interact. Okay, I'm using physics terminology now, obviously. And then what you do is you look at each cycle cover, and you take the product of the weights of all of the edges. So in this case you get a -1, in this case the product is 2, in this case the product is 1. And then you sum up all of those things, you get -1 plus 2 plus 1, and I can't do that. It's almost as bad as your math. How did I get 1? Okay, the answer to that is 2. So -1 plus 2 plus 1. Okay, so what we do now here's the kind of big picture view of what we're going to do with these cycle covers. We're going to convert looking at those Boolean formulas. So we have this Boolean formula and we want to know what's the difference in the number of phi of x equals 0 solutions from phi of x equals 1 solutions. And we're going to turn that into a graph theory problem. And the way the graph theory problem is going to work is that there are going to be certain special loops in the graph that I call external loops or variable loops. And I've drawn them in red here. And I'm going to have a big graph, and the graph is going to be constructed of subgraphs. Okay? And so this triangle means a subgraph, and this square means a subgraph. The triangle refers to a subgraph that has to do with the cubic term. The rectangles are subgraphs to do with the quadratic terms. And then the way the subgraphs are going to connect up, it matches the structure of the clauses here. So here I have a clause x1, x2, which means the variable x1, the loop that corresponds to variable x1 is going to go through this clause. So this x1, x2 clause is this one here. Okay, and there's a loop here for x2. And x2 is also in a clause with x3. So the x3 variable in this example appears in actually 3 different clauses. It appears here with x2, it appears in this cubic clause with x1 and x5, and it appears in this quadratic clause with x4, and so on. x4 joins these things and so on. So is that structure, the sort of basic structure clear? Okay, those of you who've read Valiant's Sharply complete paper will be used to seeing stuff like that. But what I'm going to do is much simpler, which I think is actually important. Okay, so what we're going to do is we're going to look at this formula, which encodes our quantum computation, and now we're going to encode a graph like that. And so as I said, these things are the external edges, I call them. Those are the variable loops, and these graph, I'm going to call them gadgets, are the subgraphs that basically do the clause. And then in our cycle covers, so remember our cycle covers are kind of sums of loops in the graph. What we're going to do is that if this loop is traversed, that is going to correspond to this variable x1 being 0. And if this loop is not traversed in the cycle cover, that's going to correspond to this variable being a 1. Okay? So that each cycle cover will either traverse this loop or it won't traverse this loop. And so you could just sort of look at the cycle cover and read off what the values were of that Boolean variable. Okay. So, what we're going to do, and this sort of is the key trick to this whole thing, and trying to make it, trying to come up with a simple graphical version of quantum computing. What we're going to do is this. We're going to make those graph gadgets, those little rectangles or triangles and so on, we're going to cook them up so that if that gadget has some vertices in it, if a particular cycle cover sort of runs through that gadget in such a way that that the external legs are not there, are empty. Okay, so remember I said if the loop is there, then the things, so if the loop is there, that's equivalent to a 0. So if the loop isn't there, that's equivalent to a 1. So in the case that, let's say this loop and this loop are not there, we're going to make this gadget sort of give an overall phase of -1 to the cycle cover. But that if one of these loops is there or both of the loops are there, then we're going to get the phase +1. Okay. So in particular, the way it would look, imagine I take one particular variable assignment to x1, x2, and x3, and so on, of 1 and 0, and so on. So imagine this was my Boolean assignment to the variables. Well then, in the graph, I'm going to cook things up so that the cycle covers have the property that this clause here, because I have 1 and 1 and 1, I'm going to get a -1 sign, because those 3 external loops won't be there, but in all the other cases I would end up with a +1 sign. Okay. So what this will do is that if an odd number of terms in this polynomial are satisfied, an odd number of the clauses satisfied, then the cycle cover will have a total weight of -1, because I'll get an odd number of products of -1. Okay? Whereas obviously if I have an even number of clauses satisfied, then the cycle cover will end up with a weight of +1. Okay? So at the end of the day, the sum of the cycle covers is going to be exactly the thing that we were looking for, which is the difference between the number of odd and number of even assignments to this formula, okay, which before I was calling number 0 minus number 1. Now, so that's the sort of the avenue of attack. What I have to do is show you that you can actually make this in a graph. Okay, so is everyone sort of happy with that? I don't know. I went through that reasonably fast. So, okay, so let me give you an example of how that rectangle subgraph would work. Okay, so here's one version of that rectangle subgraph that will work. So here are my red external legs coming in. Okay, so remember these are the things that correspond to the variable. So that if they are there, then the variable is 0. If they are not there, then the variable is 1. Okay. And what I have is an extra vertex here that has a bit of a self loop. I have some connections here, and I have, going between these two things, I have edges with a negative weight. Okay. And now let's look at the case where the two variables are 0. x1 and x2 are both 0. Okay. So if they are both 0, that means that both of those external legs are there. Okay. So if both of these external legs are there in any cycle cover, remember the cycle cover still must visit this vertex somehow. Okay, because the cycle cover has to visit every vertex, and the only way of visiting this vertex without visiting one of these guys twice is for this guy to self-interact, to have a self-loop. Okay, so the only option in the case of these two variables are 0 is this thing. Okay, and then the weight of this cycle cover, everything here, every edge here has weight 1, and so the weight is 1. Okay. Let's look at the case where x1 is 1 and x2 is 0. So if x1 is 1, that means that these external edges are not there. Okay, so I have this vertex sitting on its own. And now I've got to say, what happens to the cycle covers of this graph? Well, this external edge comes through here and takes this vertex out of action. There's nothing this vertex can do. Okay, he's got to be part of this, the rest of this cycle cover. So I get left with these two guys, and then the only thing they can do is form a loop like this. Okay? If this guy tried to self-interact, this guy would have nothing to do. You can't connect to him. He doesn't have a self-interaction term, so I wouldn't get a valid cycle cover. Okay? So this option is the only option then to those two vertices. Okay. And then in the case where both of these things are 1, okay, that means that there's no external edges here or here. And so now we actually get 3 cycle covers. Okay, we get a loop that goes around the outside things here, and this guy self-interacts. And then we get something which comes down here like that, and then the sort of the mirror opposite, this way and that way. So we get 3 terms. And then the magic is that we now get that this thing has a weight of +1, but these two both have weights of -1, So the overall weight is a minus 1. Okay? And that's what we wanted. We wanted our clause variables, like that corresponds to this clause being satisfied. Okay? Because both variables are 1. So this is a clause x1 times x2. Both variables are 1. So we get a weight minus 1. And that's how we end up finding this, the difference in this formula. Okay, so that's how the two-variable gadget works. I'm not going to go through this, but this is essentially how you deal with the cubic clauses. You have the three-variable gadgets, so you have the external edges come in, and then in this case you just need a simple triangle, and you have these sort of funny weights of minus 2 to the 1/3. Okay, but now what I've talked about has a potential problem. Okay. The problem is that I've talked about it as if every cycle cover necessarily goes, either goes around one of these loops or doesn't go around that loop. Okay. So I've sort of talked about it as if, like, well, if this goes around that loop, that's like x3 is 0. If it doesn't go around that loop, that's like x3 is 1. But it's quite possible that, maybe there's some structure in the graph such that I don't go around the whole loop. So here I just go this edge of this guy, and maybe this thing, and I don't go through the whole loop. And that's going to bugger everything up. Okay? So we have to avoid that kind of thing. And so it turns out that you can do that. And doing that is actually the sort of the most messy and complicated part of Valley and Sharp-P paper. Here it's kind of like it kind of happens by magic that you get what I think of as an interference, because I've got quantum mechanics on the brain. Of course, this graph theory's got nothing really to do with it, but I think of it as an interference which takes care of this fact. Okay, so here's the sort of interference. The thing that could screw us up is if our cycle covers could do something like this. If they could come in this edge, and instead of leaving out there, corresponding to their variable, they come in here and they leave out there. Okay, that would screw the whole thing up, because I've gone and cooked up this whole variable in such a way that it kind of triggers with a 1 or a minus 1 according to whether the corresponding edges are running through these variables like that. So, turns out though that interference kills that possibility in this gadget. So, if a cycle cover comes in here and goes out there, it's going to get a weight of minus 1. Okay? If it comes along this edge. And the only other possibility for it is that it comes down those two middle edges. And this one has a weight of minus 1 and that one has a weight of plus 1. And so those two things kill each other, and the total contribution to the sum of the weighted cycle covers is 0. Okay? So we very simply and neatly avoid that problem. Okay. So, what's the upshot? The upshot is we end up with a graph. This was the figure I showed you before. This is not exactly, of course, the particular construction I've given you, but you end up with a graph, and then you just look at that graph and you're like, well, the sum of the weighted cycle covers of that graph, okay, the sum of the cycle covers of the graph is the quantum probability that I'm looking for. And the sum of the cycle covers of the graph is given by the permanent of the adjacency matrix of the graph. So, if you're more into linear algebra, you don't want to think in terms of the graphs, you want to think in terms of the permanent. But the thing that's kind of nice when you have this is that those cycle covers no longer have a temporal direction somehow associated with them. I could give you that graph, and you wouldn't even know that what way that it was constructed, the way the quantum computing circuit flows. Okay, I could just give you the graph. The way I've drawn it there, it possibly would, but I think, in general, I could just sort of draw that graph in some way, and you wouldn't even really know what the temporal flow through the normal quantum circuit was. Okay? You're just looking at a graph and summing the cycle covers of the graph. Now, mathematically doing that is computing the permanent. Computing the permanent of a graph is obviously a nasty thing. But the thing that the sort of the end of this particular story is that my quantum probability, I can actually write it as the mod squared of the permanent of a matrix. So I can absorb even this numerical, normalization factor. I can use the fact that the permanent of a scalar times a matrix is just alpha to the n, where n is the size of the matrix. times the permanent. So I can just write the whole thing. The whole quantum probability can be written as mod squared of the permanent of a matrix. Okay? And the thing to realize is that this matrix is a polynomial in the size of the quantum computation, obviously. So it's not like the unitary matrix, like a normal quantum computation, unitary matrix is exponentially large, right? It's some unitary matrix on n qubits. It's built out of a polynomial number of gates, but it's an exponentially large matrix. This here is a matrix that's, maybe 50 by 50 or 100 by 100 or something. It's polynomially sized. If you want to factor a large number, this matrix would only have to be a few hundred by a few hundred in size. Okay.
For the exact construction that you gave, I don't see that as polynomial size, because each Toffoli gate would generate a product, and then if you compose that with another Toffoli gate, the products grow exponentially.
Yeah, so the trick to that is, it's a nice question and I glossed over it. So the trick to that is that what we can do is we can just stick two Hadamards after the output of each Toffoli gate. That gives identity. That just creates a new variable. So at the end of the day, I only get as many new variables, or two new variables, as the number of gates. Okay. Okay, so this of course is the key question about this whole talk. This is why you're here. Have I gone as mad as Bob? Why am I interested in writing a quantum probability in as simple a version of the modulus squared of a permanent as possible? Okay. I'm a physicist, I'm not a computer scientist, I don't even know what I'm doing at this conference, but obviously I have some physical motivation for doing this. Okay. So here's the physical motivation. Okay. This, at the moment, the most expensive physics experiment ever being built is about to go online, the LHC at CERN, and what it's going to do is it's going to take a whole bunch of particles and smack them together at really high energies, and it's going to create some mess like this. This is actually not a CERN picture. Their pictures are not as nice. So this is obviously a particle accelerator that is doing quantum mechanics at some level. Okay, but all it's really doing is it's bringing in certain quantum states and some other quantum states, systems and other quantum states or excitations of the field. They interact with each other and they bounce out and they go off. But then they sort of look at this mess and somehow determine, this was that type of particle and this was another type of particle and so on. But scattering of these quantum fields is a really messy thing in experiment, and it's even uglier in theory. If you try and work out the scattering amplitudes for these kinds of processes, you end up summing over a whole bunch of graphs, and it's a combinatorially really hard problem. And the theory is extremely ugly. I don't know if any of you ever had to do a quantum field theory course, but you will have been driven batty by trying to sum these kind of diagrams. And so what you might think, and what actually I think is a fascinating problem, is to try and come up with a quantum algorithm for summing Feynman diagrams or evaluating quantum scattering amplitudes in general with a quantum computer. That's a really fascinating project. If someone wants to work on it, I have some ideas. And when I sort of first put this slide up, I thought, oh yeah, that's what it's going to look like I'm talking about. But it's not. I'm going to be talking about something which is much simpler, which is then the scattering problem, where you bring in a bunch of particles and you send out a bunch of particles, is a non-trivial problem even when the fields don't interact with each other. Okay? So those Feynman diagrams are a real mess because all of these fields are interacting with each other. Okay? If you have a photon come in and then the photon can become a positron and an electron and so on, and you have to sum over all of these things. But the crazy thing about quantum field theory is that if I take a scalar field theory, so I don't even have spin and polarization stuff to worry about, I just have a scalar field, and I don't even have this scalar field interact with each other, with itself, I still kind of get a non-trivial mathematical problem to solve. So my picture of this here is that I have n1 quanta in mode 1. Okay, and n2 quanta in mode 2, and n3 quanta in mode 3. Now a mode, to a physicist, is just some degree of freedom that distinguishes this set of quanta from this one. So the mode could be the direction it's traveling in, it could be the color of the photon, It could be its polarization if it was photons, or its spin if it was electrons. A mode is just some degree of freedom that distinguishes that thing. Okay? So this here is like the most naive scattering kind of problem. I've got N1, N2, N3 quanta come in. I have now a non-interaction region, but I'm going to look at what's the amplitudes for N1 prime, N2 prime, and N3 prime quanta coming out. Okay. So you might think I've gone mad. You're like, well, these things don't interact, so how can something non-trivial happen? In fact, even though it's a non-interacting field theory, there is still a non-trivial set of transformations associated with that field theory that we call mode transformations. Okay. Now, the mode transformations are due to interference. So fields that interact with each other, they kind of like really exchange energy with each other and scatter off each other. But fields can still interfere even when they don't interact, which I guess makes sense from classical electromagnetism and so on. So photons that arrive at a beam splitter can still interfere with each other, for example, but they don't actually interact with each other. If you look at you just have a quadratic Lagrangian, there's no actual interaction terms. But the way the interference mathematically is described is as follows. You take the mode operators, okay, so some of this won't make sense if you don't know some sort of, I guess, quantum field theory, or at least the simple harmonic oscillator in normal quantum mechanics. In second quantized form, the harmonic oscillators, or the fields, have this property that they can be described by these, what we call creation operators, that act on some number of photons in mode I and kick up the number of quanta, or the number of whatever it is, photons, kick it up by one and pull out some numerical factor out the front. So these things are the creation operators for the modes, and the way you describe interference is by a unitary remixing of the mode operators. So the output mode operators are just some unitary matrix that remixes the input ones. Okay? And so now, let's consider the case of what happens when I input just one photon or one phonon or whatever my field is. I just input one in every mode, and I want to know what's the probability of just getting one in every output mode. Okay? So if I do that, well, mathematically what I do is this. I take the initial state, which is one photon in each mode. I say, well, that state is just acting the creation operator, A1 dagger, A2 dagger, all the way up to N dagger, acting on the vacuum. And then I apply that unitary transformation. So A1 dagger goes to a sum of unitary coefficients times the mode operators, a sum over the second column of the unitary matrix, and so on, like this. Okay. And now I expand out these polynomials, and I want to know what's the probability of measuring 1, 1, 1, 1, 1 on the output. Okay. Which means I've got to go through these polynomials and pick out the terms which pick out all the terms that have a single A1 dagger, A2 dagger, A3 dagger, and so on. Some of the terms will have like A1 dagger squared, and it won't have an A2 dagger, and so on. Okay, but I want to just pick out the sort of multilinear term, as it were. And so, one way of getting that is to have U11 from here, get my A1 dagger from this polynomial, my A2 dagger from this one, so I would have a term like this, U11, U22, U33, all the way up to UNN. But then another way of getting it would be to have my A1 dagger come from this polynomial, my A2 dagger to come from that one, and so on. So then I get a term like U12, U21, and so on. And then I get a sum over all permutations of these things. And so my amplitude for this scattering process is just the sum over all of those permutations and so on. And so you get an expression like this, and you're like, aha, what I have is that probability of my scattering is just the mod squared of the permanent of the unitary matrix that describes the mode remix. So we see that somehow the non-interacting quantum fields want to evaluate the permanent of a unitary matrix. Okay? The scattering amplitude is always related to permanence. I mean, if you know more quantum field theory, it's really just bosons always live in the symmetric subspace. Permanence, essentially the sort of the sum over the permutations without the kind of phases you get from fermions. So you get a certain probability of scattering amplitude. But note that this unitary matrix is not exponentially large. This is not the unitary matrix of a quantum circuit, which is a unitary matrix on Hilbert space. This is a unitary matrix on the operator space, on the space of these mode operators. Okay, so it's a small thing. Okay. So the question I had, and the question I hoped to, or the questions I hoped to be able to answer before I came to this conference was, is this problem in BQP, and is it complete for BQP? So the first question, the answer to the first question is yes, okay. This problem is in BQP, sort of as you might expect it. It's built out of quantum mechanics. And the answer to the second is, well, I wish I knew for sure before I gave this talk. Let me just convince you that sampling the modulus of the mod squared of the permanent of the unitary matrix can be done on a regular quantum computer easily. If the matrix is an n by n matrix, you can take n different q nits, so n different n-level systems, and you can efficiently create a state which is a sum over all permutations of the state. So each n-level system has, let's say, computational basis states that run through from 1 through to n. So you can create a state, for example, like this. This is a sum over all 6 permutations of 3 objects. And then if you apply the unitary matrix to each system, so you apply U, tensor U to all of the systems here, and then you work out what is the amplitude of detecting this state. So you apply the inverse of the circuit C in which you did this, you'll find that you get the mod squared of the permanent of that unitary matrix. So a quantum computer can sample that thing, which may actually be a useful thing for us to do with a quantum computer, sort of a different type of quantum algorithm. But obviously what I was doing was trying to go the other way. I showed you then that there are some very simple graphs, and computing mod squared of the permanent of those graphs encodes a quantum computation. Now, if I could find a graph which was unitary, okay, those graphs that I gave you, if you look at the adjacency matrix, they are not unitary. But if you can find a graph which is unitary, then you're encoding the quantum computation in the cycle covers, in the cycle cover of that graph. And this would actually help us build a quantum computer a lot. It would be a hell of a lot easier to build a quantum computer if we could do this. Okay? So this is why I've worked pretty hard on this problem, but it lies in some complexity class called Terry Rudolph hard. I've tried. It's not an easy thing to do. Okay, so let me just give you a final observation as to why this whole thing, you might think I've just gone and led you up the garden path and told you about this stuff, and you know, I can't tell you whether or not that sort of crunch line is going to be important or not. Although I will say that the sort of constructions I give you are much simpler than the computer science constructions of like Valiant's construction that shows that the permanent is sharply complete and so on. You can turn these kind of quantum constructions into much simpler versions of his proof. But the final observation I'll make is that it's sort of well known in quantum circles that if you have a quantum circuit built only from the control knot, the Hadamard, the X, the Z, and so on, what we call the Clifford group gates, that if your circuit's built from these things, then you can efficiently simulate that circuit using what's called the stabilizer formalism, which is where you keep track of kind of the operators rather than the states. This is called the Gottesman-Keneal theorem. And so what I noticed while I was doing all this constructing of the graphs and so on is that if I do those constructions, like I gave you earlier in the talk, for just this set of gates, then the graph that you get out is planar. It doesn't have any crossings in it. And it's well known that you can find the permanent of a planar graph efficiently. Okay? And it also maps back to just quadratic Boolean polynomials, and it's known that you can count the solutions to quadratic polynomials quite efficiently. So if nothing else, at the end of the day, I think this will give us a different version of the Gottesman-Keneal theorem. It's got nothing to do with stabilizers. It'll just give us kind of a graphical or combinatorial way of understanding why it is that you can efficiently simulate circuits built from Clifford group games. So that's basically the end of the story. I don't really have a list of conclusions for you, other than to say you don't have to be mad to be attracted to all the graphical and combinatorial versions of quantum computing, but it does help. Thanks.
Time for questions? Yes.
Kind of a naive question. You're computing every time the probability of a given output for a given input. So you'd expect you'd want to know the probability at least of all the outputs. So
No, so you can turn every BQP language to just even a single qubit, to just looking and saying, is the probability of measuring this single qubit in the state 0, is that probability greater than 3/4 or less than 1/4? And so with just some repeated sampling. So every language in BQP can be turned into just a final measurement on a single qubit. So in fact what I'm doing is even more than what you really need. I was sort of looking at a whole set of qubits at a final amplitude. But
I actually have a question. So you made this observation that computing boson scattering, even the non-interacting case, amounts to computing the permanent of a matrix, right?
Mhm.
So if you actually do the sign changes, you get the determinant instead. So does that give you fermion scattering?
Close to. I mean, it's not.
Because that's in fact easy to compute.
Yeah. So fermion scattering. Fermions are funny things. Some things are very hard to compute about fermions. Other things are very easy because they use the determinant, because they sit in the antisymmetric subspace. No, fermion scattering isn't. Yeah. Somehow it's. So the thing about fermion scattering is that it does turn out to sort of almost be completely trivial, that there isn't. That you don't get the same kind of interference at all. So I don't think it comes down to actually evaluating the determinant of the unitary matrix. I think it becomes something which is even more trivial than that. But I'm not 100% sure of that. I know Manny Knell has looked at that because people thought it might be easy to build a quantum computer, but it's easier to actually scatter fermions and bosons. But so I'm not 100% sure, but I think it's even more trivial than I think you can't even just sort of write down a non-trivial scattering matrix when they don't interact, that they really do need to interact.
Die, right? Mm-hmm. Quadratic terms are going to die automatically.
Yeah.
Yeah.
So you sort of end up with something which I think is
Fascinating.
yeah.
So you said you're not a computer scientist and you're wondering what you're doing here, but that is actually more hardcore computer science than you're likely to see the rest of the workshop. Anyway, thank you again.